First of all, let's talk about more or less around the abstract part of it, like why they came into play, what is the reason of of this paper actually. So just give me a moment. This is the abstract. So if I just read on the top right now, or like if I will go on the marking part, so if you will see, it's a basically this gradient descent, basically optimization algorithm, while increasing the popular, often uses a black box optimizer. When we say black box optimizer, it means in initial terms, when they created on the concept regarding this, they didn't know what actually is happening inside out of it. So that's why they gave us as a black box optimization. But in a practical terms, they came into the mathematical part of it, and obviously we will kind of discuss some part of mathematics here. So it's kind of a research paper reading plus math club kind of thing that we are doing here for now. I guess this is the first time that we are doing to incorporate math kind of thing here actually. Cool. So when we say gradient descent, it means descent means reducing your reductance basically, right? Reducing the gradient. When we say gradient, what is gradient at the end of the day? Gradient basically is, if you will consider in that term, differentiation of a function in a multiple respect. So, like suppose in your mathematics time, or you can say in 10th or 12th time, you pretty much know you will do differentiation with respect to some variable, right? So, suppose there is a function called z function, and you have two parameters that is depend on the z function, that is x and y. We are trying to do x and y on the basis of that basically, right? And it's very obviously it's very a basic paper around it, so I'm not even thinking around it, but think in more like a mathematical term. If we are taking an example of z is equal to f of x comma y, right? So think like in that moment, like that's what a basic aim around the version around you will see. So let's more deep dive into it, why they came into the like this concept of reducing the gradient. So why gradient came into play, we will talk around that. So in the contrary basis, what I will do is I will take an example, like kind of some data points around it, and I will try to explain that part of it. For now, like the mathematics part at the end of the day, or like I will do switch and up between one and two. But yeah, let's go to the introduction part. If you will see, so if you will see, let me go for the pen one. Okay. So the major thing is, if you will think in more that way, like gradient descent is one of the most popular algorithm to perform optimization by far, and it's basically try to work on neural networks. And the major thing is they are focused on two things, that is linear regression and lost function or cost function, depends on you what you have to say around it. I am assuming that you pretty much know about the basic thing about linear regression model and loss function or cost function. But in case if you didn't know that, think more like in a very layman term, I can share that linear regression is more like, you can think more like a y is equal to mx plus c. They work on that particular principle of mathematics. And when we say loss function or cost function, it's basically define the thinking more like as low as the loss or cost function will be, there will be good accuracy of the model. It basically show the errors between the predicted one on the real one basically. It's a concept behind it. We will deep dive that into it in the, you can say in the our machine learning boot camp basically. I guess that will be coming on the upcoming months more or less. But yeah, so cool. So now the point is how we are taking consideration it. There is a written like gradient descent is a way to maximize an objective function. So when if you are seeing this objective function is basically j basically represent, actually j represent the, just give me a moment. Okay, basically j represent the cost function, j theta represent the cost function basically, or loss function you can say. Cool. So think more like, and where theta is a kind of parameter of that particular one. Cool. Parameter of that particular of that particular function. Like generally in a function, what it describes basically, it can be data points, it can be their axis kind of thing. If we are going on the, you can say point data basically, right? And basically, if you will see, if you pretty much know it belongs to a real number, which is by updating the parameter kind of thing. And this, if you will see this part, this basically theta means gradient. Matlab, think like more like when if or, like reverse triangle is considered in a form of this, or in with any respect, like any with respect to anything. Cool. So with respect to the parameter, and there is a eta, there is one more thing called eta, that is a learning rate, which defines basically how a data point is moving, and just to move in that way. So like I will explain that also. So do not worry around it. So yeah. So now going into like what I will do here for now, maybe I just first of all jump to the, give me a moment. Give me a moment. Just give me a moment. Let me share one more tab here. Uh, Discord server one. So basically, we will right now, before deep diving into the paper, to give you a better understanding of actually how gradient descent work actually. So I'm sharing that with you. Okay. Cool. And again, if like maybe Aditya can ping me in between if there's any question, even though I know this like it's a kind of very basic algo, so there will be not as such question around it. But yeah, let's deep dive into it. So think like we are taking a data of a man with you can say they are focal, like we are taking weights and sorry, cool. Or let me go to this part. So let me remove this first of all. Okay, cool then, and let me right. Cool. So think like this. We are taking collection of weight and height of people actually. Okay. So think like this is, sorry for the cool. Okay, now think like there is different data points. Like obviously we have some particular data points. Suppose this one, this, 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 and this kind of thing. Okay, so these are some data points for now, and think like there is a line which is very kind of like any like random line basically created in between of the data point. This is a, when we say what is the equation of a line in mathematics, that is obviously this y is equal to mx plus c, right? Let me x plus c, cool. And I'm really sorry with my, just give me a moment. Okay, let me. So y is equal to mx c. Okay, cool. So now obviously we pretty much know this is the intercept. This is the intercept part of it, obviously, and this is the slope. Obviously, we know, and generally we obviously know how to, if we say how to basically calculate a slope. And when we say slope, what we actually meant is it's like think more or less in form of like, if you can understand it in that term. Suppose there is suppose we are on the top of the hill. Cool. and we are going down in the hill just to go to the lowest part of the hill. Basically, you can see the ground level part of the hill. Cool. So as we are moving downwards, we pretty much know what is the slope of the hill so that we can move faster. And if there is an irregularity in slope, suppose there is a high slope, there is a very the slope angle will be very high, so we have to do the speed. If there's very slanty, we can go faster, just we get a more inertia around it. So same thing happened here. When we say data points with the slopes, it basically tells us how a data point is traveling from one point to another point. That's why when we say what is the how we calculate slope in mathematics, right? So this is the like y2 minus y1 upon x2 x2 minus x1. That's the basically difference between the ratio of the x and y axis. Cool. Now let's consider. Let's basically go in this manner in a more depth. Let me change the color. Let me make it blue. I guess. Cool. So let's consider this for like this initial. Cool. So suppose I make it like 0.5. It's the height, and weight you can consider around maybe 1.2 for now. Cool. Now let's more understand around it, like how we can basically work on this one part. Okay, cool. So obviously this is the intercept. Obviously, now for main motto around it, consider the intercept in more like how we can make intercept, or like, because at the end of the day these are variables, like these will be changed, like in terms of like, or you can say these will be the constant on this part, right? This 0 point, this is the constant at the end of the day. We have to change slope and intercept in order to make it better, right? These are data points like weight, height. Same thing happening with different points, suppose. But like, let's consider this thing. Let me put simple value to around it. So if you will say height, that is zero point 0.5. So zero point 0.5 height, didn't have any slope till now. Cool. 1.2 will be the weight and plus c. Cool. Now understand how. Now first of all, we need to find out the slope behind it, right? That is the m. Now how we can do that? Now generally, if we calculate, like suppose if there is a equation, give me a moment. Let me. So y2 is equal to m. You can say consider y1 minus y0 divided by x1 minus x0 into uh, x2 plus c. Like this is the basic, you can say, understanding behind it. How we basically work around it, like how we basically think more or less in that format. But again, at the end of the day, this is the basic thing that how a slope works around it. Cool. Now let's find out how we can move towards with it. Cool. So till then, let me first of all let me think. Is there anyone who didn't understand the basic mathematics around it? Like you can't, you have like it's okay if you didn't know this stuff also. Like just wanted to understand. Is there anyone? Let me know. Let me go to the Discord first. Give me a moment. Okay, I guess there is no one. So okay, cool. I guess there is no one. Cool. Cool. Okay. So let's go into that front basically. So but yeah, obviously just to give you more precision, so this is the basic mathematics that I want to share with you, but this is the not the way that we are going forward with it. But yeah, so go in a more deep manner. Okay, cool. So obviously, when we say like, if you will consider in that term, like how basically everything is working around it. So in other words, basically descent basically identify the optimal value by taking big step. Is That's the major thing if we consider what gradient descent is doing basically. Cool. So think in that manner. Again, generally, suppose let's take same example within a more more better way. Cool. Let me go to the. So this is the height. This is the weight. Okay. So how will basically go forward with it? Now the point is, There is some so basically why grain descent came into play, because there's very optimization problems happening while we are going to the data set part of it. If it can be in statistics, in machine learning, or in data science also, you can say. Cool. Now the point is at the end of, so how we basically make it, like how we can understand like what is the at the end of the day we need a predicted height. If we will say we need to calculate predicted height. Cool. That's the basic agenda behind it. Cool. And if we consider, like, suppose this is a line, there is some. Let me change the data point with maybe this time green. This, 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 this. Okay. For now, it may let's take it as there is four. Okay. Now, obviously, to understand it better, let me make it to the blue part. So, and this. Okay. So obviously, we pretty much know this is the height and this is the weight, right? Obviously. So now to consider it more, we can use, like, suppose I'm taking some basically value around it, right? But at the end of the day, how we can predict the height? If we say there is a prediction, we let's say h1 is the predicted height. So how what we basically do is, like, there's some intercept, or that is, you can say intercept, or you can say c constant plus slope, right, into that particular weight, that is w, right, weight, or you can say w1, you can consider it that way. So when we say, again, that's what I'm sharing is these two are the main thing which basically learns how gradient descent can fit a line to a data by finding the optimal value for intercept and slope. That's the basic thing, because it will be the fixed. These will be the fixed one, and these will be changed on the basis of the what is the best way to basically tweak these two parameters so that we can get to get a predicted value in a more better way, right? But the more or less when we find out in that way, the if we consider, first of all, let's go to the intercept part. This part that is around, you can say, consider this as an intercept. Okay. Now we pretty much know generally. For now, let's take intercept to be zero for now. Suppose intercept is zero for now, so it will be like height. Assuming, like, we are assuming for now, suppose we are assuming that intercept is zero for now, okay, plus the slope into the weight, it depends on total. So consider like maybe for now consider it like a random thing, like slope is also you are taking around 0.64. Cool. These are the we are taking on the basis of, like, let's consider it like as an approximation part, let's consider it like that. Cool. So here we basically putting our value, height and weight, and these two for now is like we're considering like zero and slope, kind of that one. But obviously I take intercept zero, but you didn't have to take zero, you can take any number around it. But let in this example we evaluate how well this line fit the data with, so with the a particular loss function. Obviously for now I'm going with a loss function called sum of squared residual. What is the meaning of it? Residual, the height we got minus the real height, and the square of that part basically, and sum of that part basically, summation of this basically. Cool. You can say consider h1 minus h0, like they have whole square, and in the summation part of it you can understand in that manner. Cool. So, note there is a note that I want to share in machine learning lingo. The sum of squared residual is a type of loss function, that what I already shared, and obviously I just give like overlay survey around what is basically slope at the end of the day, right? So obviously we are not going there. Okay, cool. So now let's fix to the how we can predict. So let's take in consideration for now. Okay. So think like that. Consider we are taking a data point. Like if we consider this one, like let me go to the blue part. Okay. If we consider this part, we are taking a value called, like, suppose zero point 0.5. Let's consider zero point 0.5. maybe for now, this is the data point, you can say. This is action by axis. Cool. So let me go down here and think like in that format. So we have predicted height equal to 0, that is the intercept that we are taking 0.64, and the weight is here is obviously zero point 0.5, right? That what we know around. Cool. So just let's put, so it is more like, which is more like think like goes to, you can say 0.32. Cool. And if you will see in the above part, that is 1.4, like the actual height, like that is 1.4. This is the actual height. Let's go to the scene of like, let's take a difference between it. So if you will see 1.4 minus 0.32, so it will goes around, let me minus this, let me goes around, okay, let me go to this like 2, no sorry, it will goes like 1.1, I guess, yeah, 1.1, I guess, yeah. Now we will keep track the sum of the squared residual up there. So if you will see, so this is the first part of it, right? These are the difference. Now for this, the one thing, let me, okay, just give me a moment. Okay, cool. So if you consider this 1.1 whole square, the same thing happened with the other stuff also. Like if we go next to next kind of thing. So this is the first part that we got. If you will see, cool. Suppose considering, I'm just taking consideration. So for now, consider next one is like that we got is suppose 0.4 for now, like a whole square plus, and think like third one is 1.3, considering like just consider 1.3 whole and whole square, which gives around, I guess, let me calculate it on the calculator like this, it will be better one. So I am getting around 3.1. Cool. So in the end, 3.1 is the sum of the square residual at the end. So this is the function, that this is the loss function, you can say. This is the function, yeah, like think like j of theta, that what we saw in the starting point basically. Cool. Now let's go on another graph around it. Cool. So this is one more graph that I created. Okay. Now this y-axis is of j theta, that is, you can say, loss function. That calculated, that is, you can say, consider here is as how much it is, I guess 3.1, right? Let me check one more time. 3.1. So think like this is 3.1, and make it like, let me take another color for better. Okay, so this is 3.1. Okay, now this point represent basically the sum of squared residual where when intercept is 0, right? Obviously this is, if you're taking consideration this part, that is 0 basically, right? Now we consider it, there's a slash between around what is, and like something like, see, I'm just assuming like for now, like the data point is something like that, and like some data points like here, here. Like this is the general way when we say your data point is going in a better, in a perfect manner, you can say, right? I'm not going like, you can go on the mathematics part, but this is the basic thing that we are going around it. Cool. Now, obviously, for every point, there's a different intercepted. You are like initially you're 0, that will go for 0.5, this, this, that. Cool. So as you are increasing the data points around it, the kind of graph, if you will see, okay, this is the longer view I will share with you, but if we go with the, let me go to the red pen. So the data point of the same thing goes like around this one, like this kind of this graph basically. Cool. Now, the point is, at the end of the day, that the graph that we calculated for this one is has the lowest sum of the lower one. This part is the lowest. Let me go to the, this is the like the lowest part of it basically. Okay, and a slow and painful simple method for finding minimal sum of the squared residual is to plug and chug a bunch more values for the intercept basically, right? We get a lot of values around it, and obviously there's a possibility because obviously when we talk about gradient descent, so the first priority that we think is of like we can we get a less value of loss function, right? Loss function or cost function, right? Why it is there? Because we have because as slow we have a loss function, we can get a better accuracy at the end of the day, right? But when we also talk about in generalization part also, we think in a more mathematical way. So we think like if there is a local minima, if there is a local minima kind of zero, if it touches to zero, then it has one of the best like you can say your local minima is zero, or you can it tends to zero, so that means the model is kind of great, the loss function is kind of reduced to zero. Why I'm saying it? Because think like think more like this is the whole thing of j of theta. Suppose this is the cost function obviously. Suppose if I differentiate like or if I will to be very precise, let me create a gradient of theta with respect to theta of j theta. Basically what is meant I'm saying is differentiation of j theta divided by theta, you can say. Cool. And at this point, so it will be kind of a slope, like we create a like what is at the end differentiation. At the end, it signifies slope, that is tan theta at the end of the day, right? This is the slope. And if it tends to zero, when it tends to zero, when there is a tan zero, right? When the theta is equal to zero, or I guess it's 180. I'm guessing 180 or yeah, it's 180. I guess yeah, because 90 it tends to infinity, right? So if it tends to that part, that means your model is working great, it's working fine around it. Cool. That's the major motto around it. Cool. So this is what the explanation of it. But suppose we got it, but there's a possibility, right? There's a possibility that let me change the color. There is a possibility that this is also like in their neighborhood points. There is also a possibility they can also tends to lower you can say local minima, you can say, right? Which tends to zero. There is a possibility, like suppose if I will we consider this in that format like this, I'm creating another graph. Cool. And suppose there is a graph which like this and then this. Obviously, because generally in gradient descent, or if I will say the batch gradient descent, like that, what we are seeing right now, that is called vanilla gradient descent, you can say, right? If when it's equalized to zero, the gradient descent will stop. It will not move forward. So if you will consider this part, if it touches to zero, suppose, and there is more graph is already created, it will not go in the further part of it. It will totally stop where it tends to zero. There is also a possibility that maybe local minima can find out in the other part of the graph, right? That what we have to change around it. Like that's what basically gradient descent came into play, right? Now, if you consider more or less, like obviously some of like if you consider like in that format, so let me go down here. So the loss function, or you can say the basically the sum of squared residual, that is the loss function, right? So what we can do here, like consider initially we have a predicted height is 1.4, right? That is minus of you can say the calculated height, that like that's the basic the major calculated height we do. But can we do in that format like 1.4 into 0.32, right? It's the value then. But can we make it like this intercept plus 0.64 into weight, right? And this whole square, right? This is also we can do because it totally basically this what it defining. It defining 0.32, right? I just replace 0.32 with this thing. At the end of the day, we are doing the same thing at the end of the day, right? So, since this individual have a weight 0.5, and you can say like we can replace that thing, we can replace the part behind it like zero point 0.5 is the weight around it, and we can replace it. So let me go in more further around it. Let me go down. Cool. So think is like 1.4 minus Let take insert as of now for now same 0.64 into zero point 0.5, then well, cool. Now we can now plug in any value for the intercept and get a new predicted height that we want right now. Cool. But now let's focus on the second data point. Like that's the major thing is like what are different data point is there, or we can. But just like before, there's also a possibility like same thing we will do like add that part in 1.9 I guess minus the predicted one, then the whole square, right? And the predicted that we are considering same thing intercept plus 0.64 into weight then whole square, right? We can do the same thing, but just think in a just pause here just for a moment. Cool. Just suppose we have only one data point for now. Just reject this part for now. Suppose we have only this part, that is j is equal to 1.4 minus intercept into 0.64. Suppose you are also added the weight for a moment for now, you can say zero point 0.5 for now. And you are basically differentiating cost function with respect to intercept for now, right? That is dj upon di chain. If those who pretty much know about the mathematics part of it, we are using chain rule here, right? So 2 into 0.4 minus I into 0.64 into zero point 0.5, okay, plus 1.4 will be 0, negative. I will become 1, so we getting around 0.64, sorry, 0.64 into zero point 0.5, right? So if we calculate this part, so we are getting a function that is 2.8 minus 2i into 0.64 into zero point 0.5 plus you can say plus not minus 0.64, or you can say 2i minus 1. So you can consider this function in that format like 2.8 minus 2i minus 1, or 2i not minus, you can say plus 1 into 0.64 into zero point 0.5. This is the basic function that we got, and this is the gradient. This is the gradient. Basically, this is the gradient that we get from this thing. Now, why? What is the special behind this thing at the end of the day? What it makes so special around it, right? Now, if you will see here, I have a one thing that is focused on the intercept part of it, right? That is the gradient part of it, obviously, if you will consider that. But actual definition of gradient tells us around it like that. This differentiation of with respect to different parameters are gradients. Gradient, when we say when I'm writing you can say reverse triangle, right? It doesn't mean like I only differentiate this equation with the intercept. There's a possibility I can intercept that thing with my slope also, like maybe slope that can be dtheta dj by you can say dm, that is the slope part of it. So there's a you can say there's a different gradients came into play. And why I am very specific about around gradients, it's more like it depends on like this time I differentiate this time with intercept, right? Maybe next time I can differentiate with the maybe slope, or maybe x-axis, y-axis. And when I'm differentiating you can say the whole function with respect to maybe y or x-axis, that means I'm obviously it's a kind of a parameter to it, right? So when the x and y axis are also involved in that particular gradient descent, that gradient descent is also known as stochastic gradient descent, basically. Okay, to be more precise. This only if I will to be precise, there is majorly like the major used gradient descents are two types. Number one is batch one that we are doing, like we taking in a consideration of the in a whole data set we are trying to do that. And second part is the major thing, like you can say stochastic gradient descent. We are basically doing part by part by part. Cool. So this is the thing that we solve, and if you will consider it more or less like this is the how it totally works around it. But if you will consider it on a graph point of view, so let's go back to on the graph part. Cool. So suppose consider maybe I created a graph again. Like let me change the color to be cool. This is the graph, and suppose this is the cool. This one point where you can there is a slope behind it, or you can say if you consider local minimum of this function f theta. Suppose cool. Now this is the graph that I created for the residual part of it. That is the why it is square because the sum squared loss function, right? Difference difference between the two parties x0 x1, yeah, h1 minus h2 kind of thing. Okay, so we are doing on the same part now. The major thing is this is the major thing that we are doing around this is the major part of gradient descent. Now understand in a more better way. If I will choose you, let me go back to the paper part of it for now. Cool. Let me just give me a moment.